In this problem, we have a Falcon 9 rocket launching out of Cape Canaveral. It, included in its payload, has a mass of 535,000 kilograms. And we have information about this start of its flight. In the first 30 seconds, it gains altitude and speed. And we're looking for the total power output of its engines. Now, it's got 9 engines, but they didn't want the total power, so we don't need to worry about the number of engines in here. But let's look at a classic power example. All right, so if we draw this rocket, on the launch pad, right, you've got your rocket here, and it's got, some kind of engines down here, whatever they are, right? And later, that rocket is going to be elevated, and it's got those engines here firing, and it now has velocity, but it also has gained this amount of height, right? So if we're looking at the energy at position 1 compared to the energy at position 2, right, well, energy is conserved, right? You can't gain height and velocity without energy, but the type of energy that it has at the launch pad is just stored, right? Potential energy in the form of all the fuel, right? It's got all this frozen, liquid oxygen in there. It's going to be fired, but later the energy has been changed. Right, at position 2, we ask ourselves, well, is it elevated? Well, yes, it has GPE. It also has motion, so it has kinetic energy. It might still have some stored fuel potential, but what the energy has changed, right? When we look at the work done, work is equal to the change in energy. And the way the energy has changed, it has been converted to kinetic energy and GPE. So if I want the change in energy, I need the total amount of energy in the form of GPE at 2 plus the kinetic energy at 2. That would be the change in energy. And our equation would be mass times gravity times the height at 2 plus 1/2 the mass times the velocity at 2 squared. That would be my total change in energy. So I'm going to plug in some values. I have 535,000 kilograms times 9.8. And they have 1.5 kilometers. Let's make sure we get that to meters. That's going to be, right, if I convert 1.5 kilometers, it's going to be 1,500 meters. There's my GPE, plus 1/2 of 535,000 kilograms times the velocity they gave me, which is 100 meters per second, and we'll square that. All right, so let's pull out a calculator. Let's get some work done here. We have 535,000 times 9.8 times 1,500. That's our GPE, big number, plus 0.5 times 535 times 100 squared. And when we add that together, boy, we got a big number. 1.05 times 10 to the 10. Our change in energy, the amount that has been converted to GPE and KE, is 1.05 times 10 to the 10 joules. But they want to know the power output, right? And power is the work done over a period of time, or remember, work is the change in energy, which is what we just found over time. And since we know the time is 30 seconds, well, then power is going to be equal to the change in energy, 1.05 times 10 to the 10 joules, divided by 30 seconds, the time it took to do that work. So if I take my number and I divide by 30, I get the power output, right? And we get, looks like a lot of zeros. I count 1, 2, 3, 4, 5, 6, 7, 8, 3.51 times 10 to the 8 times 10 to the 8 watts, right? So a lot of power out of that engine. That would be an acceptable answer. You might convert that to kilowatts. You might convert it to horsepower. There's different units for power, but that would be ultimately the power of the rocket engines to get it up to that speed and at that altitude in 30 seconds.